This is the second part of the Energy, Power and Climate Change unit, and in this unit we're going to be looking at nuclear power. So nuclear power, commercial nuclear power, currently is confined to just nuclear fission power. Most of our nuclear energy is produced by the fission, the splitting of uranium-235, which is a relatively rare isotope of uranium. The process of fission is induced by a neutron. A neutron is captured, and the result is that the uranium-235 nucleus splits into two daughter particles and also produces on average 3 neutrons. The important thing is that these neutrons that are produced can go on to produce more fissions, so it can generate a chain reaction. For this chain reaction to happen, we have to have a critical mass of the uranium-235 present. It's just enough so that each uranium-235 fission produces 1 neutron, which goes on to generate more, or 1 more uranium-235 fission, so the reaction is stable. If more than 1 neutron is captured and causes fission, then the reaction will accelerate, and if less than 1 neutron is captured per fission, then the reaction will gradually slow down. So what we want is what we call a critical situation, whereby the reaction is stable and constant. Something which would be supercritical would possibly be an explosive situation, not in a reactor though, because reactors don't have sufficient concentration of uranium-235 to explode, but a supercritical situation could lead to meltdown and increasing temperature of the reactor core. Critical mass isn't just due to mass. The shape of the piece can affect whether it is critical or not. Also, whether we have a reflective layer around the piece can affect whether it's actually reaches the critical mass situation. So as I just mentioned, we want to maintain this critical situation whereby 2 of these neutrons, if 3 are produced, are captured or absorbed, and 1 will go on to produce a subsequent fission. So uranium is in most nuclear reactors, and it's uranium-235 which is fissionable. But where it is mined, the percentage of uranium-235 out of the ground is actually pretty small. It's around about 0.5% compared to the amount of uranium-238. So it's necessary to actually enrich the uranium to increase the percentage of uranium-235. Otherwise, it's just not possible to reach a critical mass situation. So the uranium comes out of the ground as an oxide, and it has to be converted into uranium hexafluoride so that it can actually be enriched. Normally enrichment has to occur in a gas form. Centrifuge or diffusion techniques are used, but it has to be in a gas. Uranium hexafluoride is a gas. After it's been enriched, the fuel pellets are fabricated, goes into the reactor, produces the electricity. It can be reprocessed because plutonium, as we'll see later on, is actually a byproduct of the reactor process, making the electricity. So we can actually reprocess some of the fuel. Waste fuel is a bit of a problem, but we can encase it in glass and metal and store it underground for a very, very long time. So this schematic shows a nuclear reactor, and we can look at the energy transformations that occur. We've got the fuel elements, the fuel rods here, and these fuel rods generate a lot of heat. What happens is the fission fragments have kinetic energy, and they are rapidly stopped by the surrounding material, which causes the material to get very, very hot. So the fuel rods get hot. This heat is transferred to the heat exchange fluid, which we can see in this blue circuit here. So it goes round and round, and the heat is removed from the reactor core. This heat is transferred to a water circuit here, which produces steam, which turns turbines, which generates electricity in the regular method that thermal power stations, fossil fuel thermal power stations use. We can see a concrete shield around the whole thing. We want to contain this, isolate all of these, the nuclear parts, the parts with the ionizing radiation. Let's just have a look at this applet from PHET, Colorado. This shows a population of uranium-235 in amongst uranium-238. Normally the enriched situation would be about 3% uranium-235, so this diagram is not to scale at all. When I send in a neutron, we can see that a small chain reaction occurs. We have an initial fission, neutrons are produced, and those neutrons fly off and cause subsequent fissions to happen. Now we can also see here that we have uranium-238 left over, but we also see we've got uranium-239 produced as well, which fairly rapidly decays into plutonium-239. This schematic of the actual reactor itself shows us a couple of other features of the nuclear reactor. This feature here is the control rods. The control rods are needed to actually control the rate of reaction. If I have the control rods fully inserted and I try and start the reaction, it rapidly comes to a halt because these control rods absorb neutrons. If I remove the control rods completely out of the reactor core, we can see that the reaction rapidly increases and we get a large power output, possibly hotter than we actually want it to be, which could generate a meltdown situation. So we actually position the control rods in such a position that we get the desired power output. The fuel rods are also inserted amongst a moderator material, which is sometimes a special kind of water, heavy water, made out of an isotope of hydrogen or graphite. And what this does is it slows the neutrons down. The neutrons, when they are released, simply have too much energy. They need to be slowed down to around 1 electron volt, otherwise they have too much energy to be captured and too much energy to produce the fissions. So we need that moderator substance. So just summarizing a few things, we can see here on this diagram we've got a fuel pellet, just to give you an idea of the size of this thing. These are stacked up together in fuel rods, large numbers, and then into fuel assemblies. And these are the things which actually go into the reactor core. So this diagram again shows the circuit which is removing heat from the core, which then transfers heat, the heat transfer to the steam circuit here to generate the necessary kinetic energy for the turbine and the generator. The control rods, they're very dense material. They can be raised or lowered to control the rate of reaction. The moderator slows these neutrons down, and the heat exchanger removes the heat from the reactor core. A little more on neutron capture. So the uranium-238, which is not fissionable, can capture neutrons, which are produced by the fission of uranium-235, which produces uranium-239, which decays 23 minutes to neptunium, and then 2.36 days from neptunium to plutonium. So it doesn't take very long to produce this plutonium, which is then stable on average half-life of 24,000 years. So this plutonium can actually be used in nuclear reactors as well to generate electricity, generate the heat needed, which is a good thing. Unfortunately, the bad thing is that plutonium-239 is one of the main isotopes used for nuclear weapons. So a peaceful uranium-235 nuclear reactor is actually generating plutonium-239, which could be used in weapons. So there are some problems associated with nuclear fission. Thermal meltdown is a possibility. It's very rare. It has occurred due to some mistakes or possibly earthquake, tsunami situation, as in Fukushima recently. Nuclear waste, very hazardous material, and it can last a long time. These isotopes have very long half-lives, so it has to be disposed of in a special way, normally underground, encased in glass and encased in metal and encased in concrete. Mining is hazardous, but uranium mining is extra hazardous because of the isotopes that are being dug out of the ground. And as also mentioned, a byproduct of the fission of uranium-235 is plutonium-239 by neutron capture of 238, which can be used to produce nuclear weapons. And finally, nuclear fusion. Nuclear fusion is something which we would love to have a good handle on. We are not producing any viable energy from nuclear fusion at the moment. We'd like to, because hydrogen is plentiful. The byproducts are not as harmful as with nuclear fission, but there are problems. We're talking about 10 million Kelvin reaction temperature, which needs to be contained. It's normally contained, this hot plasma is contained in a donut magnetic field. But at the moment, we're not getting a positive energy output. We're putting more energy in than we're actually getting out. But this is the process, generally speaking, which is used in the sun, and if we could harness this, we would certainly be onto a winner. But it's a work in progress.